Hi friends, today we are going to solve this kth missing positive number. Okay, let me read question for you. So we are given an array of positive integer sorted in a strictly increasing order and an integer k. Got it? Return the kth positive integer that is missing from this array. That is also good. Okay, so what is the array? Array is this numbers and k is equal to 5. It means we need to return the fifth missing number. Now, what are the fifth missing number? 1 is missing, 2 is there, right? 3 is there, 4 is there, 5 is missing, 6 is missing, 7 is there, 8 is missing, 9 is missing, 10 is missing, 11 is there, 12 is missing, likewise so on. Okay, so what we need to do? We need to return fifth missing number. Now, if you see, this is an array which says what numbers are missing in our original array. So if you see 1 is missing, 5 is missing, 6 is missing, 8 is missing, 9 is missing, and if you count 1, 2, 3, 4, 5, this 9 is the fifth number which is missing. Means when k is equal to 5 in this array, starting from 1, you can return that number and that number will be your answer, right? So how you can do that? I'll first share the linear approach and then we'll optimize it till the point we can optimize. Okay, so what we can do means one way is to solve this problem in order of k. Then I'll share the next in order of n. Then next I'll share how to solve this problem in log n time. Okay, so if you see, uh, to solve in order of k, why I'm saying order of k, let me go through algorithm once, let me write code for it, and then I'll explain why it's order of k. Okay, so let's say we have one counter. Okay, and we are iterating over indexes as well. So idx is equal to, let's say, 0. From 0th index will be calculating. Now while k is greater than 0, till that point we need to run. What we need to run? We need to increase count. Means we are going to count 1, 2, 3, 4 and check if that number is present in our array or not. So idx is less than len of nums, and what else? And nums of that idx is equal to the count, current count. Means if we are at 1, we'll be checking 1 is present at first index or not. If not, means let's say if present, then what we are going to do? We are going to increment our index to 1. Else what we are going to do? Else we are going to subtract k by 1. Means one number is missing right now. So the point means at the point when k will be 0, you'll be encountered k, means k missing number already encountered, so you can return just count and that will work fine. So here if you see, it depends on k. Why it depends on k? Because this is of if you see, this condition will be applicable for n times, but in rest of the time you are checking for k elements. Let's say k is equal to 10,000, then you need to run this else condition 1,000 times, right? So it's not purely dependent on index. Means it is more of dependent on the k. So that's why the complexity of this algorithm will be uh, big O of n plus k. Okay, mainly depend on k, because k is if k is much greater than n, then big O of k. This is the condition. Now I'll run this algorithm and show you it will work fine. Then I'll optimize it for you. Okay, what's the problem? Okay, nums. All good. I have added few more test cases to be correct every point. So that is the thing. Okay, so I can submit it and say that this algorithm will work fine. And then I'll go for optimization. Okay, now what will be the optimized code? That is, I'll be deleting this. Now what else you can do? you can do one thing, like let's say index is equal to len of nums minus 1. You are starting from rightmost index, that is last index. Okay, now till what point you are going to run? You are going to run while idx is greater than equal to 0. Beyond that, there will be no index, right? So at this point, let's say you are here and you wanted to check how many elements are at this position. Means if you are at this position, I wanted to know how many missing number beside 11. If you see, let's say your array is like this. I'll just copy and explain you here. Okay, let's say 1 and 2, then 3, then 4, then 5, 6, 7, 8, 9, 10, 11 is missing here. So 11, 12, 13, and so on. Let's say this is your original array. And if you see any number you can pick, like let's say you are picking 5, then 5 will be at index 4, right? 0, 1, 2, 3, 4. If 5 is at index 4, it means there are 0 missing elements. So how you can calculate that? You can do one thing, 5 minus 1 means the current number. I'll write here again, nums of that particular index minus 1 minus the index itself, I dx itself, will give you count of missing numbers before that, before missing number before itself, right? So with this we can apply logic here. If what we need to do this, if this is the thing, then and that is greater than or equal to k, means let's say you are searching for some number and the missing number is exactly equal to k or greater than k. It means let's say you are here and you found out that the missing element will be in between 7 and 11. So what you are going to do one thing, go to 7 and check how many numbers are missing before 7. So let's say for a while, let's say assume that 3 elements are missing before 7. Okay, and now you wanted to calculate 2 more, and you know that it will be below 11 only, not beyond 11, within limit of 11. Means the count will be less than the missing number at 11. So what you can do, you can pick this 7. Okay, subtract what are the missing elements, that is like 3. Yeah, you can subtract that missing elements. uh, i'll I'll rerun, means what I want to say is like I'll explain you with example. I'll let me write example here, because with that means simulating real case will work fine, assuming that will not work, right? Let's say you are at 11 and you wanted to check how many numbers are missing before 11. So if you see 11, it is at index 0, 1, 2, 3, 4, fourth index, right? So 11 minus 1 is 10. 10 minus fourth index is equal to how many numbers? Is equal to 6 numbers. 6 number are missing. So what you can do, you can go ahead one more step and check for 7. And if you check for 7, 7 minus 1 is 6, minus third index is equal to 3. It means the 7 is number at which 3 number are missing before that. But at 11, 6 number are missing and we are searching for fifth missing number. means that will be in between, that number will be in between 7 to 11, right? So what you can do, now you know that three numbers are missing. You are at index 4, right? Sorry, index 3. You are at missing numbers before 7 plus. Three numbers are missing till 7. You encountered four elements. So idx of 7 plus 1, that will be 4 number, right? Now 3 plus 4, in total we are able to encounter 7 number in this array, right? Now missing numbers are 7, okay, and k is 5. So what you can do, you can calculate one more thing, like k minus missing numbers is equal to number, a number which will be basically that number if we add that number with this expression, will be getting our missing number. Like this will be 2, right? So what you can do, 2 plus, means you can add 2 here. We calculated 4 number, we calculated this 3 number, now we need 2 more numbers, so we'll be adding this, means this 2 number. So in total your answer will be like this, like missing numbers, okay, plus this. Now missing number 7 before 7 is will get cancelled off. So our index will be the index of 7 plus 1 plus k. That will be your answer. So what will be, I'll keep it here. I'll just copy it and write in next line. Okay. So now is your answer. What is index of 7? Index of 7 is 3 plus 1 plus k is 5 is equal to 8 plus 1 9. So 9 is your answer. Okay. You can do same thing with k is equal to 2. Let's say we have four numbers. Okay. Four numbers and k is equal to 2. So what you need to do? You need to run it for 4. Now if you check for 4, how many numbers are missing? So 4 minus 1 and index of 4 is 0, 1, 2, 3. That is 3 is equal to 0. 0 numbers are missing. Means this is the rightmost index, and we encountered like k we wanted is 2, but the means the missing number we can calculate till this point is 0. So what we need to do, we need to calculate, uh, you can do missing number before 4. That will be, I'll just copy this and update it only. Okay, so missing number before 7 plus index of 7 plus 1. Now k minus missing number will give how many numbers are required. So missing number before 4 is 0, k is 2 is equal to 2. Now missing number before 7, not before 7, before 4 is 0. Means I'll just write this, and this will boil down to this algorithm, right? And if you see the missing means index is 3 plus 1 plus 2 is equal to 6. So this will give you your answer, right? Means we need to do this only. I'll be now writing the code. If nums of index minus 1, that missing number is greater than equal to k, it means I'm going to decrement my index by 1. Okay. Else what I'll be doing? Do I need to do anything? No. Okay, I'll be just sub yeah, going to that index, and what I'll be doing is else break. You don't have to do anything. Now at the end you need to return this, and that boil down to this equation. So index of 4 means the position we stop will be the index. Okay, so index plus 1 plus k will give us answer. Idx plus 1 plus k will be our answer. I'll try to run it. Yes, I'll submit it. Okay, now if you see, the complexity of this algorithm is order of n. It's purely depend on this index. Index is grading decremented each time. Means the loop is not dependent on k. It's dependent on the length of nums, right? At the end, you just have to return this algorithm. Oh, sorry, this equation. And how we derived this equation, you can see each time how we calculated that number. So this is what an algorithm that will be of order n. Now, how you can optimize this as well needs to be a question, right? Means here there is one follow-up like, could you solve this problem in less than O time complexity? How we can solve that? So we are sure that now our index means we need to find the index just before that our element will exist, means the missing number will exist. That's it. The problem boils down to that question only. How we can do that? Means we are checking linearly here. Can we do something else? Can we do like let's say left pointer and right pointer, and it's equal to 0 to len of nums minus 1. Okay, you are here, and while left is less than right. Okay, I'll be with me. I'll let you know why each step I am doing. Okay, now you'll calculate mid first. Mid will be left plus right by 2. Okay, if now at mid index nums of mid minus 1 minus mid is greater than equal to k. If that is the case, then what we are going to do? If that is the case, then we are just shifting our right index by 1, right? Means if we are at particular index and we saw that that index is greater than equal to k, then we are leaving that index and going leftward direction. So what you can do, you can do one thing, like you can move your right pointer to mid minus 1. Else else what we are going to do? Now we'll see else what we can do. If let's say you are solving for this question, okay, and you encountered that mid is 4, and if you check for mid is 4, what will be the number of missing element before 4? 4 is at index 2. It means 4 minus 1, yeah, 4 minus 1, here if you see 4 minus 1 is 3, means it needs to be at index 3, but it is at index 2. It means one element is missing. If you see just one element is missing, then this is something from where you need to go right and check for the index where the means at this point you are just यहाँ पे आपको ये पता चलता है that your answer will lie between 4 and 11. You are not sure whether it will be between 4 or 7 or 7 or 11. So you need to go deeper. How you'll go deeper? You need to move your left pointer where your left pointer needs to be. That will be mid plus 1, right? Now your mid pointer will be at 7. Now if you are at 7 and 11, you calculate mid will be at 7th index, and if you calculate again, so it's again the less means At 7, 7 minus 1 is 6, 6 minus 3 is just 3. Means just three numbers are missing. So we need to check whether our answer will be in between 7 or 11, or it will be between 11 and infinity. So how you are going to do? Now you are going to move your left pointer to mid plus 1. That will be 11. Now left and right pointing to 11. But what we want? We don't want to stop here, and we want to go, means we want to find a index where our uh, pointer will be at 7. So what you can do, instead of left and right are pointing to same element, let left and right cross each other. Okay, so now if you see, 7 and 11 are sorry, left and right pointer are pointing to 11, and mid will be 11 only. Now what will be the number of missing elements? 11 minus 1 is 10. 10 minus fourth index is 6. 6 numbers are missing, means your answer will be in left of 11th index. So what you can do, you can move your right to 7, because your right will be moved to 7th, the index 3. Here your solution will stop. Now what you need to do, your right index, right index is the position which you wanted, so you just have to return right index plus 1 plus k, and that will give you your answer. So you can remove this much code. Okay, you need to run this, and this will give you your answer. Now you know how we went through order of k solution, order of n solution, and then order of log n solution. Why log n? Because each time you are just dividing your search space into half and half. Means this is just a version of means a tweaked version of binary search. Binary search, how or when you need to apply binary search. Means the thing is, whenever there is a case where you can divide your search space into two half, you can apply binary search. And you know the complexity of binary search is log n. And what will be the space complexity? If we talk about space complexity, we are just using some variables, right? Means that will be of order 1. So you need to come up with this intuition. Means how you are going to solve this, how you are going to uh, come up with this thing, right? If you are able to derive that, means you are uh, means you can solve that problem. That's so easy, right? So you need to think the way I showed you right now. And with this, yeah, one day I'll be also a great engineer, and you too. See you. Bye. See you, and all the best. Bye bye.